Remote Learning 20, Part 2. Okay, so now it gets a little more interesting. So I'm going to introduce you to this idea of continuous mass density. So this is the idea that instead of having a bunch of point masses or discrete masses along the x-axis, we're going to have some sort of object lying on the x-axis. And this object is going to have variable densities. So it's not uniformly dense. It might be more dense on one side than the other, or it might be more dense in the middle and less dense on the edges. And of course, then we would need some sort of function that describes the densities at some x value to help us out. But that's the idea, that we're going to have along the x-axis a rod of some kind, but it's going to not be of uniform density. Okay, so let's get a picture here, and what I'm going to do is have this x-axis go, but let's see, what's my best way to do it? I can alter the height in a minute if I need to. Okay, and then in order to enable some drawings that are going to happen later, I'm going to increase the thickness of this x-axis, but we need to sort of think about it as being not thick, because we're going to stick with this one-dimensional idea here for now. Okay, so this is my weird x-axis, and it's going from we're going to be interested in it anyway, from some A point to some B point. And what I'm saying is that on one end of it or the other, the density is going to be different. And the density is going to be found by knowing the density function. And that's what this is. Okay, so let's just read it out here. Instead of discrete masses arranged along the x-axis, suppose we have an object lying on the x-axis between A and B. At point X, suppose the object has mass density, and then that density is this function. Okay, so this symbol, this is what mine will look like as I progress. But this symbol is the lowercase delta. Okay, so it's D for density, but we're not using uppercase delta. That's change in. Okay, so just so you have an idea of I mean, that can be helpful to know that that's representing, the letter D. Okay, D for density. That's our density function. All right. So in order to find the center of mass of this sort of object, what we're going to do is we're going to chop this thing up into n many little sections, all that are going to have a width of delta x. So I'll have, one here, one here, one here. I'll have so many. I'll have n many of them. All right, you can probably see the integral notion coming your way. Then what we're going to do is we're going to run n to infinity and shrink delta x down to 0. And then introduce the idea of the integral. Okay, so why are we doing that? Well, again, this has variable density. So I can find the mass of this, or maybe I should say I can approximate the mass of this, because I know the density is going to be pretty much uniform over this delta. But it's not. The smaller the delta, the less the error in terms of calculating the mass. So that's the cornerstone idea, that in order to calculate the mass of any particular strip, you need it to be infinitely thin, because its density is different on the left-hand side than it is on the right-hand side. All right, so let's get to thinking about the mass of just one strip. So the mass of the ith strip, then you could think about that as the one that I've drawn. So we could call this place x sub I there. And the mass of this ith strip is the density at that place times delta x. So let's think about the units. They've told us that this density function is mass per unit length, right? So let's go with something like grams per centimeter. And then this change in x is going to be measured in centimeters. And okay, so then I get mass in grams like I'm supposed to. All right, so just wanted you to think about the units there. All right, so we've got the mass of the ith strip. So if we then want to broaden this to the formula that we introduced you to in terms of finding x bar, I want you to recall that x bar is equal to, okay, so it's equal to the various masses times the various displacements summed together divided by the sum of all the individual masses, and that turns out to be total mass down there. Right, so just take you back a couple of pages. That's this idea. Okay, so we did it with 3 point masses, and now we're going to broaden that to infinitely many point masses of different densities. All right, so coming back over here, so here it is again. And the next thing to think about is, well, what are the masses? So let's get into here, and that's the mass of the ith strip. But if you want to sum together all of the strips, then you need to think about using the density component. So this is the density of some random strip times the width of some random strip. So I just laid out the argument where that is the mass. And then we're going to sum all the masses, and if you will, we'll go from 1 to n. And then we have the n many strips' masses summed together. So that would be the mass of the object. All right. So meanwhile, up on top, we're going to sum together, again, running from 1 to n many such strips. And if we can use our formula over here, we're just going to swap out mass for delta x dx, if you will, delta x, right? A little weird, times another x. Okay, so I'm going to write that x part first, and then we're going to multiply that by the density function evaluated at some x value times the thickness of the strip near to that x value. Okay, so variable density, a function that describes the density being this delta of x. And all right, so this is our center of mass formula, x bar. Okay, that'd be for n many. Now let's go to infinitely many. Well, I think we do the usual thing, so we'll just write it out over here. As n approaches infinity, then delta x approaches 0. And then just to reiterate, that's removing any error And we have error because the density is not the same over this entire delta. So the smaller the delta x, then the more accurate our modeling is. Okay, so then I'm not going to roll through all of the argument as we once upon a time did, but then that leads to down below the integral of the density function from a to b, and up on top it's the integral of x times the density function from a to b. Okay, so our delta x's became our dx's, and there you have it. Okay, so that's a pretty complicated scenario all of a sudden. Let's roll into a sample problem to see if we can help it sort of take root. Okay, so find the center of mass of a 2-meter rod lying on the x-axis with its left end at the origin if, and then I'll just do A here, the density is constant and the total mass is 5 kilograms. All right, so let's get a visual on this. And I'll just throw out a 2-meter long rod. There it is. And it says that its left end is the origin. So I'm going to call this 0. I'm going to call that 2. And here the density is constant. And the total mass is 5 kilograms. So I'll just underline that so I don't have to rewrite it. Okay, well, if the density is constant, then I can tell you it's going to balance right here in the middle. So then we know that x bar is equal to 1. And there are no point masses on it. It's of uniform density. All right, but what we want to do is we just want to roll through this argument and confirm that x bar is equal to 1. And then I'll come over here and we'll do things as they get a little more complicated. All right, so x bar. X bar is equal to the integral from 0 to 2 of x times density. I'm going to write it out here, density function dx. And then that's divided by, well, there's a couple ways to think about it. I could certainly just rewrite all this. They didn't give us a density function, so that's why I'm avoiding writing it. But, you know, it's the sum of the masses. The sum of all of the masses is the bottom. So I'm just going to write total mass. Okay, so on this one, we know that the total mass is 5. So then all we need to do is we need to really concentrate on is what is the density function? Okay, well, density is mass divided by length. In a one-dimensional case, it's mass divided by area. In a two-dimensional case, and it's mass divided by volume in a three-dimensional case. But here, our density function is equal to the mass divided by the length. And it's just a constant. Okay. And I could have done that on bottom, just rewrite an integral without the x, but then when I compute the integral, it'll take me to 5. All right, so let's just extend this page a little bit. And we've got x bar, which is now equal to, okay, so we're going to pluck out the 5/2. I'm going to recognize this divide by 5 as 1/5. And then I am going to integrate x, that's x squared over 2. And I'm going to evaluate that from 0 to 2. Okay, so 0 gets zeroed out. And I can do a little bit of math over here. Okay, so when I do all of that, I get 4 over 4. And okay, it turned out to be 1, like we knew it was supposed to be. I feel like I want to come up here and modify this a little bit. And just right here, this is ending up to be the total mass. And this is, I suppose we can write it the sum of the moments. Mass times displacement. Right? These make mass together. All right, so let's go on to B. And I think it's probably a better idea to just give us some room. Okay, so let's see. Now we've got a density function. So I'll start with that drawing again. And going from 0 to 2. And x bar is going to equal, all right, so we've got the integral from 0 to 2 of x times the density function, which they gave us this time, dx. And then on bottom, it's the integral of the density function, dx. Okay, so let's just think through what these things mean one more time. When you take density measured in kilograms per meter, right? Think about the units of that, times a infinitesimally small length, but a length nonetheless measured in meters, then this is going to wind up in kilograms. So we're summing all of these masses together. So we've got total mass on bottom, and the same argument leads me to this represents mass, and that is displacement. Okay, so this is the sum of the moments. X bar, sum of the moments divided by the sum of the masses. All right, so let's see what we can do on this. What is this? This is 15x cubed, running from 0 to 2, and I'll just rewrite this one. This was 15x squared, running from 0 to 2. I'll just work this way. Okay, so let's see. We take out the 15, we take out the 15. Those cancel each other out. All right, so that's one thing that can happen. Now I'm going to integrate this one. That's x to the 4th divided by 4. And then I'm going to integrate this one, and that's x cubed divided by 3. All right, and both of those are evaluated from 0 to 2. This one gets zeroed out. And what is that? That's 16 over 4 for 4. And then over here, that one gets zeroed out, and then that's 8/3. So 4 over 1 times 3 over 8 is 3/2. Okay, so then that's 3/2 meters. So we're going out to 1 and a half and marking that as x bar. Okay, so let's see if that makes sense. All right, so how does that make sense to me? So we're looking at a density that is more dense on this side than it is on that side. At this side, the density is 0, right? Because you put in 0. And at this side, the density is 60, right? So it's more dense out here. So, and it's heavier on this end. So then it makes sense that the center of mass has shifted towards that direction. Okay, so this is obviously like really heavy group of notes, but I want to read through it and then do this last problem here down at the bottom in the 10 minutes that I have here. Okay, so I'm moving on to 2 and 3 dimensional regions. For a system of masses that lies in the plane, the center of mass is a point with coordinates x bar, y bar. In 3 dimensions, the center of mass is a point with coordinates x bar, y bar, z bar. Okay, fine. To compute the center of mass in 3 dimensions, we use the following formulas. And then this, I think, is the tricky part, this sort of a sub x, a sub y, a sub z stuff. So let's catch this. To compute the center of mass in 3 dimensions, we use the following formulas, in which a sub x of x is the area of a slice perpendicular to the x-axis. Okay, and a sub y and a sub z are defined similarly. In 2 dimensions, we use the same formulas for x bar and y bar, so these same formulas. Okay, but now it's 2 dimensions, so a sub x and a sub y are defined a little differently. A sub x and a sub y need to be interpreted as the lengths of the strips perpendicular to the corresponding axes. All right, and then I'm going to do one of these 2-dimensional ones next, so I think that'll help clarify things. All right, so I'm just going to roll right into this. Find the coordinates of the center of mass of the isosceles triangle in the figure below. The triangle has constant density and mass m. All right, so we did just talk about variable density, but when you start to get into 2 and 3-dimensional objects with variable density, then you're looking at calculus 2 because you're looking at some double integrals. So we're going to hold off on that. All right. So let's see, I think I might end up writing on this. So I'm going to make that a little bit bigger. And we're going to use those formulas up there. So, okay, so fine. Let's go find the center of mass. The center of mass, in terms of notation, is x bar, y bar. So we need to find each of those. All right, now I'm going to argue right away that y bar is 0. And that's due to symmetry. And the fact that this is 0, 0. Okay, so there's symmetry. There's an equal amount of area above and below. So this thing is going to bounce at this height, which is the height y bar. You know, you can just think about this as a cutout piece of cardboard. You have a stick, it's going to balance right there. So that's a symmetry argument. And that's y bar. All right, so x bar is a little bit tougher, obviously. So x bar is equal to, so let's go grab its formula. And it's the integral of x and density. So it's not density of x, it's just density. And that's a constant, right? Because it's telling us that there's constant density. And but then there's this feature, a sub x, which is the length of some strip perpendicular to the x-axis. We should probably draw that. All right, so some arbitrary x place, and I draw a strip there and start marking things up. Okay, so we can talk about this as being x sub I, and we can talk about that as being delta x. Okay. So just following the formula, this is the sum of the moments. So we've got the displacement, and then this density times the height of this strip, which is what this represents. We haven't calculated it yet. times its width, these three things make the mass. So in terms of the definition of a moment, it's mass times displacement. All right, so let's do that again. This is density. This is height. This is obviously the width. And that then is the mass. All right, the mass is found by calculating the density per square unit of measure and then times the area, because we're going two-dimensional here. Okay, then on bottom it's the sum of the masses, and so I don't know, I'll just call that total mass. All right, so let's see what's happening with this one. Find the coordinates of the center of mass of an isosceles triangle. The triangle has constant density, which equals this, and mass m. Okay, so I know the bottom is m, so I can do that. Just sort of glance right past this integral. It's going from 0 to 1, right? That's where we can position these strips anywhere from 0 to 1. All right, so then we'll come back over here. We've got 0 to 1. We've got x. Okay, can we come up with what the density is? All right, well, density equals the mass divided by the area in the two-dimensional sense. So what do we have for mass? We have m. What do we have for the area of this? Well, it's a triangle, so it's 1/2 base times height. The base, well, I guess we can go this way as base and this way as height if you wish. All right, but so it's 1 and 1. So that makes the density 2m, m divided by 1/2. Okay, so I now have density in here. All right, but then what is the height? Well, the height keeps changing as you slide your strip around, but for the ith strip, the height is, well, I suppose it's twice whatever the equation for this line is. Okay, so now I got to go back to algebra 1 and get the equation for this line. So that's y equals mx plus b. The slope appears to be down 1/2 and over 1. So that's negative 1/2 x plus the y-intercept, which is 1/2. Okay, so that's the equation for that, which makes the height of the ith strip 2 times y sub I, because y sub I is calculating just this one. All right, and then so what is that? That's all those get multiplied by 2, so negative xi plus 1, 1 minus x dx. Well, let's compute. I think we're pretty much there. All right, I'm just going to come down below because it looks like I got some nice room down here. And I can cancel out the m's. And the 2 can come out. And it looks like I got a pretty easy integral. It is x minus x squared. Okay, so let's not forget the 2. That's turning into x squared over 2. Reverse power rule. Same thing with this one, but x cubed over 3. Running from 0 to 1. That one's going to zero everything out. I've got 2 times 1/2 minus 1/3. Okay, so a half minus a third is a sixth. And it looks like I'm at 1/3. Okay, so 1/3. And where is 1/3? That's, well, in fact, that's listed as a coordinate. So center of mass is 1/3, comma 0, which is about, that's a halfway marker, so we're just going to go right about here. Okay, that's our center of mass. All right, and again, that feels right because if you were to try to find, if you were to think about where you would sort of put your finger underneath a cardboard cutout of this, clearly it would be left of the halfway marker because there's more of the object over there. Okay, I'll throw some problems your way to practice using these new ideas. Thanks for your attention, and reach out as you need to, no problem. All right, so then here is assignment part 2. It's certainly more meaty than assignment part 1. There are 4 problems in total, and I'm going to ask you to really make an effort to draw a good drawing, make good labels. I understand that there's a formula associated with this stuff, but please definitely avoid just trying to just start throwing things into the formula without making a drawing. So it's just all about process. Try to make 4 really good solutions, including, of course, computing the integrals. Okay, thanks, and feel free to reach out for help.